This lesson begins our start of quadratic functions, and so it's going to be broken up into several different parts. But when we look at quadratic functions, we're going to focus on two different forms of the equation. So we have this one, and then we have this one. Both of those are going to be important. The first one has ax squared plus bx plus c. That is our standard form. So standard, or sometimes called general form, of our quadratic function. The graph of a quadratic function, as we've talked about, is a parabola. A parabola usually looks like this, but sometimes it goes down, but it will make that U shape if a, that leading coefficient in front of the x squared, so if a is greater than 0, our parabola opens up, and if a is less than 0, our parabola opens down. And that's because it was reflected across the x-axis. The vertex of our parabola is our maximum or the minimum. So it's the maximum of a downward parabola, and it's the minimum of an upward parabola. The graph is also symmetric with a vertical line drawn through the vertex called the axis of symmetry. So when we think about a parabola graph, it is symmetric and it folds right down the middle. That is called our axis of symmetry. The vertex, let's put that right here, is going to be labeled a point HK, and that's just the x value and the y value. We gave it some letters, but it is the vertex. And then it's based off of these coefficients that we see there to get your HK. All right, the vertex form, or the transformation form, is our first blank. So the transformation form of a quadratic equation. However, another name is called the vertex form. So I often refer to it as a vertex form, but it's nice because it shows us the transformations that have happened. And since that's a lesson that we just talked about, I'm going to start there. If we have a function in vertex form like this, we can see some of the transformations that occurred. Like this -3 went right 3, and it went down 5. The 2 was that vertical stretch by a factor of 2. So that gives us an idea just of the overall shape that we're working with. In this one, the direction of opening is up, and that's because our a value is greater than 0. So because a is greater than 0, our a in front is 2. The vertex, if we follow the form, it's supposed to be hk. Now we have x minus h. So x minus 3, that means h is 3. Down 5 made it move -5. So even with the transformations, we saw a point go from 0, 0 to right 3 down 5. It goes to +3, -5. And then the y-coordinate of the vertex is a maximum or a minimum value. Because this opens up, we have a minimum. And our axis of symmetry. So if you sketched it out, we'd see a parabola that has a minimum here at 3, -5. And if I fold it right down the middle, that x value tells us our axis of symmetry. So our x equals 3 is the axis of symmetry. When you're writing this axis of symmetry, you don't want to put just 3. If I put just 3, then I'm going to get it wrong because 3 is just a number. The axis of symmetry is a line. It's a vertical line, so we want the equation of it, which means I need an x equals for it to be an equation. Example B here has another transformation, but we see something that moved left 2 and up 4. The difference here is that it says x plus 2 and not x minus a value. And that's because this this plus came from minus a negative 2. Because if I had minus a negative, that does make that plus. So the h value is a negative 2. It still went up 4, so k is 4. I'm just going to rewrite it this way so that we have the whole function. But our function, our parabola, will be opening down this time. So this is down because a is less than 0. The vertex would be negative 2, positive 4. And if we kind of sketched it, I'd go from 0, 0, go left 2, up 4. And we know it's going down. We also had this vertical shrink by a factor of 1/3. So what's happening here is that it's actually making it look fatter, but it's squishing that vertical component, so it's shrinking it down. Now when I look at the y-coordinate of the vertex, it is a maximum because it's flipped over the x-axis. And then our axis of symmetry is our x-coordinate, so we have x equals negative 2 from our vertex. That's where it folds right down the middle there. We want to put all this together to describe our key features and to sketch out a graph. Now, we don't have to have a graph or have to know how to graph to be able to describe all these key features, but it is helpful to be able to just put this equation into our transformation form and describe those different transformations. So I'm just going to go ahead and put in here, we know it moved right 5 and down 7, which makes the vertex 5, negative 7. It does have a vertical stretch this time because of the 2 out there, so we're going to say a vertical stretch by a factor of 2. A factor of 2. And it wasn't flipped, so we know it's going to be going upward. It doesn't ask about the direction of opening yet, but it will be helpful when we graph. The axis of symmetry, where it folds, is going to be that x equals 5 because of the x-coordinate of our vertex. And then increasing, decreasing, domain and range, all of that can still be done if we kind of have an idea of the sketch of a graph. So even if we didn't make a full graph, it would be helpful just to sketch and put our vertex 5, negative 7, and you would know that it's increasing on the right side here. So that's all the x values beyond 5. I would say 5 to infinity. It's decreasing for all the values below 5, and we're always reporting our x values when we're describing increase and decrease. So the values below 5 would be negative infinity all the way to 5. We always go least to greatest. And then we get to our domain. Our domain is all real numbers because it's a quadratic. Quadratics will never have a domain restriction because they're not going to put a square root in here. We're not going to get square root of x. That would become a radical function. We don't have a rational function, so if it's just a quadratic like this, it's always going to have a domain of all real numbers. The range, however, depends on where it was shifted. So it shifted down 7, and it's still opening up. That means that minimum value is going to be negative 7. That's the lowest it's ever going to reach. So our range would go from negative 7 all the way up to infinity. And we could sketch at any point. So before I actually do sketch, I want to look at the parent function y equals x squared. So if you had the parent function, let's just do this in red. And I did input output. Hopefully you know this graph, but you will definitely want to practice it. So it would start at 0, 0, and then if I go to 1, 1 squared is 1. 2 squared is 4. So we graph our point there. 3 squared is 9. We have a point there. We can't go 4 to 16 because it's off the graph, but that's enough to give me a general shape on the right, and because it's symmetric, it would do the same on the left. So we still go out 1 from the vertex, go up 1, out 2 from the vertex, and up 4, because 2 squared is 4. Out 3, up 9. So there's our general shape. And we can use that transformation rules to create our graph. So I'm going to make the actual graph here in purple and move this vertex right 5 and down 7. So I'm going to go right 1, 2, 3, 4, 5, down 7, 1, 2, 3, 4, 5, 6, 7, and put our point. And then we can start doing our other coordinates. Now, we had a vertical stretch, so a normal parabola is just going to go out 1, up 1, out 2, up 4, out 3, up 9, because it's just the squares. But with our parabola, it had a vertical stretch by a factor of 2. So instead of going out 1, up 1, the vertical part has to be multiplied by 2. So I'm going to go out 1 and up 2. And then when we go out 2, it would normally go up 4, because 2 squared is 4, but we're going to have to multiply that 4 by 2 to get the vertical stretch. So that becomes out 2, up 8. So 1, 2, 3, 4, 5, 6, 7, 8. And we put our point. Out 3 squared is 9, so it would typically go up 9, but we stretch it by 2, so that becomes 18. So out 3, up 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 is just off the graph there, but we can kind of figure out where that point would go. It's still symmetric, so we're going to just use the same pattern on the left side. So out 1, up 2, out 2, up 8, and out 3, up 18. So there's our really skinny parabola. And it's skinny just because of that vertical stretch. So you want to have a couple points so that you can create the best parabola that you have here. But I want to at least put in the notes how we found those points. So we started at our vertex, and then this was our general parabola. So we went out 1, up 1, and then we went out 2, up 4, and so on, out 3, up 9. But for the new one, we took that point and it got steep. So I went out 1, up 2, out 2, up 8. So you can see those vertical components were stretched. So that made that vertical stretch by a factor of 2. Let's look at the next one. And so we have a transformation that's still in vertex form. It moved left 1 and up 8. The negative in front is what's doing our reflection. So that should automatically tell us it's going to go down. But there was a vertical shrink. Let's go ahead and put the vertex in here. It moved left 1, so that's a negative 1. Up 8 goes positive 8. But it's a vertical shrink by a factor of 1/3. So vertical shrink by a factor of 1/3. It's not a factor of negative 1/3. The negative is what's doing the flipping, the reflecting across the x-axis. The 1/3 part is the vertical shrink. Our axis of symmetry would be x equals -1 because that's the x coordinate of the vertex. And then we can decide where it's increasing and decreasing. So if I put my vertex here, I'm at -1, 8. The increase is going up here on the left. So that would be all the x values from -infinity until we get to that -1. And then it starts to decrease. So it would decrease from -1 to positive infinity. Again, these are going to be parentheses. We have a parentheses at -1 because it's turning at that point. It's not increasing, it's not decreasing, it's turning directions. All right, the domain is all real numbers like we've seen. It's always going to be all real numbers for a parabola. But the range, this one's flipped this time. So now the y values are going to go all the way from -infinity until you get to the highest y value, which would be 8. So parentheses -infinity all the way to 8 with a bracket. Now you could wait to do the increasing, decreasing, domain, and range, all that thing, after you've graphed this. So that would be one option. I'm going to go ahead and put in the vertex. So I'm going to go -1, +8, and we have our vertex. But when I do this and follow the transformation rules, I would typically go out 1 and down 1 since it's reflected. But we had a vertical shrink. So instead of going out 1, down 1, I need to shrink that by 1/3. And 1 times 1/3 is just 1/3. So I'm going to go out 1 and down 1/3. And I can do that on both sides because it is symmetric. Now if I go out 2, 2 squared is 4, but that 4 is being shrunk by a factor of 3. So it's down 4/3. Now 4/3 as a decimal is 1.333. So I'm going to go out 2 and down 1 and 1/3 to get my 4/3. Do it the same on the left side. If I go out 3, 3 squared is 9, so I would typically go down 9, but we shrink that by 1/3. So 1/3 of 9 is 3. So I'm going to go out 3 and down 3. 1, 2, 3. Put my point. You can keep doing all of these points. And if I go out 4, 4 squared is 16, but I need to shrink that 16 by 1/3. If you noticed that 3 came out as a nice point, all of the multiples of 3 should give us nice coordinates because we're going to be multiplying by 1/3. So the next multiple would be 6. So I'm going to go out 6, 1, 2, 3, 4, 5, 6. I'm going from the vertex every time. So out 6 from the vertex, and 6 squared is 36. But I want 1/3 of that. So 1/3 of 36 is 12. So out 6 from the vertex and down 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It would do the same on the left here. Let's see, out 1, 2, 3, 4, 5, 6. You could do 9, you could do 12, and just as far as it would let you go on from your vertex. But that's a lot of points already, so I'm just going to sketch out what we have. And there's our parabola. Again, to put this in our notes so that you have an idea of how we got this without a calculator, we followed our general parent function. So I would go out 1, down 1 to get a point. Out 2, down 4. Out 3, down 9. And that would be our parabola. But we want to make that shrink. So let's put that in here. I'm going to go out 1 and down 1/3. Out 2 and down 4/3. Out 3 and down 3. So that gives us our vertical shrink. If by a factor of 1/3. So I would try that out. Find some of the examples in our lab manual where you're just looking at the transformation form and describing these key features, and then try to graph this without a calculator, but by using your transformation rules. A word problem here that is in vertex form is helpful to notice. It's not often that you're going to see these word problems in vertex form, but we do have one, so let's at least make a note. Because there is a benefit to being in vertex form. We want to know that the profit function here is made from an item that is a function of the number of items in thousands sold, and is modeled by this function. So our output is our profit, our input x is the number of items sold. And we can see our vertex automatically because we have that transformation. So our vertex is going to be at 4, 5, because it moved right 4 and up 5. It was also flipped, so I know that the graph is going to look something like this. But because this is a word problem, it's helpful to actually sketch it out. And when you pause to sketch, even though it doesn't ask you to, what that's going to do is help you kind of make sense of the problem so you're not going so fast through it. But the x-axis is representing the number of items in thousands. And we moved right 4, 1, 2, 3, 4, up 5, so 1, 2, 3, 4, 5. We put our vertex there. The y-axis is our p of x, so that's our profit. And it says that that profit is in millions of dollars. So millions of dollars there. But we want to put in the rest of our graph. So we know it flips down. It also has a vertical stretch by a factor of 3. So I'd go out 1, down 1, 2, 3. And we have a pretty steep parabola. It'll look something like this. It's not supposed to be perfect, but it does help give us some context. Because when we answer these questions, what is the maximum profit? The maximum profit is our y value. That's the 5. So 5, if you just put that as the answer, would be counted wrong, because it's not just 5, it's $5 million. And then how many items must be sold to achieve that is our x value. Again, we have to think of it in context because it's not just 4. It's 4,000 items. And then state the interval where the profit is increasing. So our increasing section is on the left. But when we think about this in context, we're not going to say negative infinity all the way to 4. We're going to think about what are the possible number of items that we have. And there's no way that we could have a negative number of items that we're selling because we haven't made them. So our minimum, our lowest x value possible would be 0. So I would say from 0 all the way to whatever that highest point is, which is 4. So from 0 to 4, it would be increasing. There's our increase. If it asks about decrease, it'd be from 4 to infinity. Theoretically, we could keep making infinite number of items, but there may be some limitations on that. If we just look at this interval notation, it doesn't actually give us much context. So I'm going to write this out in a sentence or word format. So from 0 items to not 4, but 4,000 items. Because that 4 doesn't really tell us the whole picture since our items are in thousands. The next video will go through some standard form information.